Let's talk about tangent planes and linearizations. I mean, a couple people have already kind of asked me about whether or not this is kind of the same thing as when we did linearizations in 17A. And yes, it is pretty much exactly the same process, or I should say it's analogous to the process. It's very much the same. We're just kind of adding on an extra piece. So let's look back at an example just from before. So in 17A, if we wanted to find the equation of a tangent line to the function y equals f of x at the point x naught, y naught, we would have done it like this. We would have said, well, y minus the y coordinate equal to the slope, which is f prime at x naught times x minus the x coordinate. And that's how you could find the equation of the tangent line. And then if you need to isolate y, you're certainly welcome to. Similarly, and really, so I should point out, the tangent line equation and the linearization are really the same thing, just written in a little bit of a different way. So let me write the linearization of f of x at, we typically say x equal to a, although using x equal to x naught is also perfectly fine. I'm just taking this equation and rewriting it. I'm rewriting y as L of x. I'm adding y naught to both sides, but instead of calling it y naught, I'm calling it f of a plus f prime of, instead of x naught, I'm calling it just a times x minus a. So we're just replacing every x naught with a and isolating L of x. That's right. So this here, right, that's our y naught. That's our f prime of x naught. The point being, it's really the same equation. The tangent line equation and the linearization are the same thing. So if we were asked, whoops, pen's all over the place here. If we were asked to say, find the linearization of f of x equal to the square root of x at a equal to 9, and then use it to approximate square root of 10, here's what we do. And I would really think of doing this without drawing any sort of picture, although I am going to draw a picture after we do it. So we would really just kind of fill in the pieces here. Our a is 9. Our f of x is the square root of x, which is x to the 1/2. And we're also going to need f prime of x. F prime of x is 1/2 x to the negative 1/2, or if you prefer, 1/2 root x. So that f of a, or f of 9, is just the square root of 9, which is 3. And f prime of a, or f prime of 9, is 1/2 root 9, which is 1/6. And now we have all the pieces we need to write the linearization. The linearization is equal to f of a, or f of 9, plus f prime of a times x minus a. Here's a good tip. Unless you're asked to, it's usually in your interest to not simplify this. I don't want to write this as mx plus b, right? We could write y equals 1/6 x, and let's see, 9 times 1/6 is 3/2. Minus 3/2 plus 3 is plus 3/2. That's not super helpful, because when I plug in x equal to 10, it's going to be much nicer to have plugged it in here than plugging it in here. So even though you could do this, and sometimes, especially if you're like answering these questions in web work, they will give you like the simplified version of the equation of your tangent plane. It's still good to write it like this, or the expanded version. So even though this is fine, we don't really want this. Now, if I want to approximate the square root of 10, this linearization is the approximation of my function. And here's the picture before we actually plug it in. So the idea here is that our function, f of x equal to the square root of x, looks like this. And we're looking at what's happening at 9. We're drawing the tangent line at 9. I've got it on a ruler so I can draw straight lines. So there's our tangent line. That's our linearization. Same thing as our tangent line. And now what we're doing is we're saying, well, if I plug in x equal to 10, instead of finding the square root of 10, which would be the value on the function, I'm going to instead go just a little bit higher and see what I get on the line. Because it's really, really close to the square root of 10, but it's much easier to calculate. Right? If I plug in 10 to my linearization here, L of 10 is just going to be 3 plus 1/6 times 10 minus 9, which is just 3 plus 1/6, which you could leave like that, or you could write it as a mixed fraction, 19/6. But really, I want to write it as a decimal, which is 3.16666 forever. And the reason I want to write it as a decimal is because I should have done this ahead of time. If you look at what the square root of 10 is, like if you use a calculator and find the square root of 10, it's going to be 3.162 approximately. So the point here is that the linearization giving us an estimate of 3 and a 6, or 3.16 forever, is a pretty good estimate of the actual square root of 10. So that's why you might do something like this. Oh, sorry. I don't love that. I don't love this. Oh, well. If things are in the way, just let me know. I will try to be better about that. So that's the idea, right? That's what a linearization is. And now we're just going to extend that idea to another dimension. So, oh, and by the way, here's the intended form. For those of you on Zoom, I just would recommend going to Canvas. So now, let's say we want to find, in a similar way, the tangent plane to the surface f of xy at the point x naught, y naught, z naught. And I would probably write this as z equal to f of xy at the point x naught, y naught, z naught. It's literally the same equation as before. We're just going to add in an extra piece. So instead of doing y minus y naught equals the derivative times x minus x naught, now we're going to do z minus z naught equals the derivative with respect to x. I don't usually like to write the at x naught y naught here, but we can write that. So there's the slope in the x direction times x minus x naught plus the slope in the y direction at that point times y minus y naught. And also, like before, we can then find the linearization by just solving for z and calling things different names if we feel like it. So the linearization L of xy, that's what z is going to become. So we're going to get L of xy equal to z naught, except we're going to call it f of x naught, y naught, because you find z by plugging in x and y to get the z value. And then plus all the rest of this. Fx at x naught, y naught times x minus x naught plus fy evaluated at x naught, y naught times y minus y naught. So it's virtually the same thing as what we did in 17a. There's just like an added piece. Instead of a derivative times the x minus x naught, it's this derivative times that plus also the other derivative times that. But it's really not different. Questions so far? Okay, let's look at some examples. So let's say we've got the following. Let's say we have this. I'm trying to keep things on the screen here. Let's find the linearization of f of xy equal to x cubed times y to the fourth at the point 2, 1. So what you should be thinking of, right, is we're finding the equation of the tangent plane. This surface has, at this point, there is a plane that is tangent to it. The process is not terrible. I'm going to find my partial derivatives. Fx is going to be 3x squared times y to the fourth. Fy is going to be x cubed times 4y cubed. And then I do want to plug in these points. So fx at 2, 1 is going to be 3 times 2 squared times 1 to the fourth, which is 12. And fy at 2, 1 is 2 cubed times 4 times 1 cubed, which is 8 times 4, which is 32. And then I'm going to write it all out. So I probably should also find f of 2, 1, right? Because I need the f of 2, 1. That's the first piece right there. So f of 2, 1 is 2 cubed times 1 to the fourth, which is just 8. So writing out my linearization here, f of L of xy, it's going to be f of 2, 1 plus the derivative in the x direction times x minus the x value plus the derivative in the y direction times y minus the y value. And that's the whole thing. I don't want to simplify this. Here's why. So you could totally write this as, 12x plus 32y plus, I don't know, whatever 8 minus 24 minus 32 is. It's not really helpful. And here's why it's not helpful. Typically, you're going to be asked to then use the linear approximation, the linearization to approximate, estimate if you prefer, f of 2.2, 1.9, which would be 2.2 cubed times 1.9 to the fourth. Could you find that? Sure, it's not impossible, right? 2.2 cubed is something we could multiply out by hand if we didn't have a calculator, but that's not the point. We don't want to do that. The idea here is that this is going to be approximately equal to L of 2.2, 1.9. Just like in the previous example, right? We plugged in 10 and we found the value on the straight line, which was 3.16666, and it was close to the actual square root of 10. Same idea here. I don't want to find the actual value of this. I'm going to find this instead, which is much easier. Look, if I plug in 2.2 for x, I'm going to get 8 plus 12 times 2.2 minus 2 plus 32 times 1.9 minus 1. And that's why we don't multiply it out. Because I don't, 1.9, sorry. Ooh, did I make a mistake here? Apologies. I think I did make a mistake here. Sorry, I meant for that to be a 0.9. I apologize. I read that wrong. Sorry. You should be plugging in points that are relatively close to where you're linearizing it at. It should be a 0.9. Sorry about that. So then 2.2 minus 2 is just 0.2. And 0.9 minus 1 is negative 0.1. I'm going to multiply this out. I get 8 plus 12 times 0.2 is 2.4. And 32 times 0.1 is, well, it's minus 3.2. So I end up getting 7.2. And so what we're saying is whatever this function value actually is, it's pretty close to 7.2. And it should make sense that if this surface is not super weird and like really discontinuous, if the surface is fairly smooth, then if we pick a value of x and y that are close to 2 and 1, the output shouldn't be that far from 8. And it's not that far from 8. I should mention that if someone instead said, take this whole thing and find the equation of the tangent plane, I would probably write it as z minus the z value equal to my slope in the x direction times x minus the x value plus my slope in the y direction times y minus the y value. I don't know why that's a standard way of doing it, but it's fairly standard. Yeah. So those were given, right? Like so like if someone's asking you a question like this, they're gonna say, find the linearization of this surface or this function of two variables at a particular point, 2, 1 in this example, and then they're going to give you some other point close to 2, 1 that you're being asked to use the linearization to estimate the function value. But it's totally like, it's just, we're picking it out of thin air, right? I could have just as easily said, use the value like, I don't know, 1.7 and 1.3, right? That would have been also a good thing to check. Other questions? Yeah, Jocelyn. Right, they're the actual values, where x and y are the variables. Let's look at another example. So I will say this linearization thing is not that terrible. It's pretty straightforward once you've done it a few times. It's just kind of rinse, wash, rinse, repeat. You're doing the same thing over and over again. There's not really a whole lot of variety to it. It gets a little more challenging if your function is harder to differentiate, but that's kind of the only real place where this gets tough, in my opinion. So let's say we want to find the equation of the tangent plane to z equal to 4x squared minus y cubed plus 2xy squared. Oh, I did something dumb. That's fine. At the point, sure. 1, 2, sure. I changed some things. So I had to, yeah. And if you check, if you plug in 1 for x and 2 for y, you should get 4 for z. It's not a bad idea to check. If you plug in 1 for x, like 4 times 1 squared minus 2 cubed plus 2 times 1 times 2 squared. I'm getting 4 minus 8 plus 8, which is indeed 4. That is your f of x naught, y naught. Right there and right there. It's just the z value when you plug in the x and y coordinate that you've been given. Okay. Did I? I did. Yeah, sorry. This the directions. Find the equation of the tangent plane to this. Okay. So I want you all to try this one. So I will remind you, your equation should look something like z minus your z naught, or your f of x naught y naught, equal to the partial derivative evaluated at x naught y naught. This is another way of writing that you plug in x naught y naught. This vertical line means take the partial derivative and then plug in x naught y naught times x minus x naught plus the partial with respect to y evaluated at x naught y naught times y minus y naught. Go ahead and give that a try. I'll give you a couple minutes to work on that. You guys at home too, or wherever you are on the Zoom, you guys on Zoom as well. Give this a try. remind you, you need to use the product rule when you take the derivative. Oh, no, that's a whole lot of lying. Never mind. There's no product rule here. I'm a big liar. I was imagining something else. Be about 20 more seconds, and then we'll go over it here. All right, let's go ahead and see what we've got. So first I'm going to find the partial derivatives first. So my partial derivative with respect to x. Again, I'm writing fx, even though I haven't called anything f. I'm making kind of just the assumption this is my f of xy. If you don't like that, you could also just call it zx instead. That would also be okay. It's just a name. The other way, the partial of this with respect to x is going to be 8x plus 2y squared. And then if I plug in my point, which is 1, 2, I'm going to get 8 times 1 plus 2 times 2 squared, which is 16. In a similar way, I can find fy or zy. And that's going to be, let's see, now it's going to be negative 3y squared plus 4xy. And if I plug in my coordinate of 1, 2, I'm going to get negative 3 times 2 squared plus 4 times 1 times 2, which is negative 12 plus 8, which is negative 4. So then my equation of the tangent plane is going to be, and a few people ask me about this one, like there was on the web work when they're writing the equation plane, you have to write like z equal to something or z minus the value equal to something. There has to be, if someone says find the equation of something, you have to have something equal to something else. It can't just be what the function is. It has to be something equal to that function. So I'm going to write it as z minus 4 equal to my fx, which is 16 times x minus 1 plus my fy, which is negative 4 times y minus 2. And then someone could ask the question, use this to now approximate f of 1.3 comma 1.9. Values that are relatively close to the actual given values of x and y. They shouldn't be too far away. Otherwise, your tangent plane is very different from what the actual surface looks like. Just like back in our very first example, right? If you move way far away from the point of tangency, the function and the linearization move farther and farther apart from each other. So the further away you move from the point, the less good your approximation is. So here, just plugging that in. So I've done something kind of funky here, is that I want to approximate this, but I haven't actually written what the linearization is. I found the tangent plane, but I should say that the linearization L of xy is, I'm solving for z and calling it L of xy. So my linearization is 4 plus 16 times x minus 1 plus, I should have written minus, but I didn't, minus 4 times y minus 2. And now I'm going to use this linearization to approximate f of 1.3, 1.9. It's going to be approximately equal to the linearization at 1.3, 1.9. Which is going to be 4 plus 16 times 1.3 minus 1. I think you could probably skip the step of writing 1.3 minus 1 and just write 0.3 plus negative 4 times 1.9 minus 2. So here we've got 4 plus 16 times 0.3 is 4.8. Negative 4 times negative 0.1 is going to be positive 0.4. Yeah, right? Yeah. And that's going to equal 9.2. So quite a ways from the value of 4, which goes to show that, right? We might have a surface that's very, very steep at this point. So if you move away from it, it's going to get very, very different very, very rapidly. That happens sometimes. Okay, so now we're really about to do just the same thing again, but kind of twice at once, if that makes sense. Here's what I mean. We're going to talk about vector valued functions because sometimes that's something we talk about in this class, and clearly that is something your instructor is covering, so we should talk about it. It's not that big a deal. So what is a vector valued function? It's literally just a function where both of the, sorry, or I should say, it's literally just a vector where both of the entries are functions of, in this particular paradigm, typically x and y. So here's an example. We write our function with an arrow over it to indicate that it's a vector. Yeah, sure. So we're going to say the vector valued function of x comma y is equal to, let's make something that's not too terrible. Let's say we've got 3x squared minus 4y for the first function, and sure, 7x. That's going to be kind of boring. Plus 3y for the second function. Okay. So we want to find the linearization for this vector valued function. The linearization for the vector valued function f of xy is written as L with an arrow above it of xy. The vector valued linearization of the x and y. And here's all it's going to be. Oh, I need to pick a point, right? We can't just say the linearization anywhere. You have to decide where we are linearizing at. So let's say we want to find the linearization of this at, let's say, the point -1, 1. The short answer to this question is we're just going to linearize each function separately and then write the result as a vector. So let's just do them piece by piece. For the first part, and I'm going to call this first part, people often call this f1 of x comma y and f2 of x comma y. So for the linearization of f1 of x comma y, we're going to say that L1 of x comma y is the usual thing. It's going to be f1 of x naught y naught plus the partial derivative in the x direction. I should say f1x, the partial derivative of f1 in the x direction at -1, 1 times x minus -1 plus the partial derivative of f1 in the y direction at -1, 1 times y minus the y coordinate. Got to go, Maddie? Okay. I mean, you're welcome to go, but no, you're welcome to do whatever. Just yeah. Okay. So then looking at my first function, which is 3x squared minus 4y, f of -1, 1 is going to be 3 minus 4. The partial, and so let's write some partials over here. The partial of f1 with respect to x is going to be 6x. The partial of f1 with respect to y is going to be -4. So f1x of -1, 1 is going to be -6. So I'm plugging in -1 for x and 1 for y into that partial derivative times x plus 1 plus the partial derivative at -1, 1. Sorry, the partial derivative with respect to y at -1, 1 is just going to be -4. There is no place to plug in the point. So we're just going to get a -4 times y minus 1. That's our linearization of the first part with respect that at -1, 1. Let's do the second part now. So, and to be proactive here, let's go ahead and write down. I'm sorry, if you can't see something, please let me know. I know I'm kind of going off the edge here occasionally, so don't hesitate to be like, hey, James, I need to see that. Let's find our partials of our second function. So the partial derivative of f2 with respect to x is going to be 7. And the partial derivative of f2 with respect to y is going to be 3. So when I find my second linearization, or the linearization of the second piece of this vector valued function, it's going to be f2 of -1, 1 plus the partial with respect to x at -1, 1. There isn't anything to plug in. So I'm just going to get 7 times x minus minus 1. And for the partial with respect to y, it's equal to 3, no matter what I plug in. So I'm just going to get 3 times y minus 1. So the linearization of the second piece of this vector valued function is going to be, the f2 of -1, 1 is -7 plus 3, which is -4. So it's -4 plus 7 times x plus 1 plus 3 times y minus 1. Kind of a lot. We're going to make it a little bit less a lot in a minute here. So here's what I would say. Our overall vector valued linearization is just equal to this right here that I'm boxing in green here. This is the first row of our answer, and this second part here in red, this is the second row of our answer. So the vector that we're going to write is going to be -4. Oh, geez, I started writing the wrong thing first. Oh my goodness. -1 plus -6 times x plus 1 plus -4 times y minus 1. And the second entry is going to be -4 plus 7 times x plus 1 plus 3 times y minus 1. And I think I can make this fit, so I want to make it fit. So check this out. This is equal to -1, -4 plus, okay, check out this matrix multiplication here. The coefficient matrix, -6, -4, +7, +3 times x minus the x coordinate, y minus the y coordinate. That is the same thing. So you can kind of do this whole process in a shorter way. I've definitely done it kind of the longest way possible. But yeah, let's do a different example and see how we could have made this process a little bit faster. Let's say we've got another vector valued function. Let's give it a different name just for fun. Let's call it g. Let's say the vector valued function g of xy is equal to, sure, we've got like 8x minus 2y squared. And the bottom part is going to be, yeah, let's do that, 5x squared. And we want to find the linearization of g of xy at the point, and just really making something up. Let's say 1, 3. So here's the shorter way of doing this. Our linearization, L of xy, there's kind of 3 pieces to it. There's the first vector here, which is really just your original vector evaluated at the point, g of 1, 3. Right, I'll point out back, so I'm going to go back and forth a little bit here. If you look at this previous example, if you plug in -1, 1 to the vector valued function here, which you can't see that I'm pointing to, sorry. If you plug in -1, 1, you exactly get 3 minus 4, which is -1, and -7 plus 3, which is -4. You exactly get this first part right here. So to get that first part, I'm just going to plug in 1 and 3, and I'm going to get, let's see, well, if I plug in 1 for x and 3 for y, I get 8 minus 2 times 9, which is -10. And I get 5 times 1 squared, which is 5. That's the first piece. So that's analogous to this piece right there. And now I'm going to add on a matrix times I'm gonna write down here. A matrix times x minus the x coordinate, y minus the y coordinate. And what we call this matrix here is we call it the Jacobian. The Jacobian of your function. The Jacobian of a matrix is just all of the partial derivatives with respect of each function with respect to each variable. So the Jacobian here is, and again, that's why it's important to give some notation here. If we call this first piece G1 and the second piece G2, I always think about it as we want the derivative of G1 with respect to x, and then we want the derivative of G1 with respect to y. And then in the next row, you want the same thing, except you want the derivative of G1 with respect, sorry, G2 with respect to x, and then the derivative of G2 with respect to y. And I should back up here for a second, because there's something I realized that I should make sure everyone's okay with. I know you're supposed to have talked about in 17b, but would anyone like me to talk about matrix multiplication for a minute? Or is everyone okay with matrix multiplication? Okay, well, I'll address it in a second here. So in this particular problem, if I want to find the Jacobian here of this function g, it's going to be the partial derivative of the first piece with respect to x. So that's going to be 8. Partial derivative of the first piece with respect to y, that's going to be negative 4y. And then, oh, and I have my notation here is a little wonky. I'll fix it. The partial derivative of the second piece with respect to x, so 10x. Partial derivative of the second piece with respect to y, which is going to be 0. And sorry, I should say, we usually don't write the Jacobian of the function. That's kind of not great notation. What they should really be writing is we want to find the Jacobian at the point 1, 3. And so if we plug in 1 for x and 3 for y, we get 8, negative 4 times 3, 10 times 1, and 0. So our Jacobian here is 8, negative 12, 10, 0. But all we're really getting here is just all the partial derivatives at the particular point. So this is just the derivative in the x direction at our given point of the first piece. This is our derivative of in the y direction of our first function. This is the derivative in the x direction of our second function. This is the derivative in the y direction of our second function. And so when we write this out, our linearization as a vector valued function is just going to be negative 10, 5 plus 8, negative 12, 10, 0 times x minus 1, y minus 3. That's the compact way of writing it. But let me write it out for you the long way so you can see the same thing we saw before. All right, I'm going to leave that up there. So if I was going to write this out the long way, here's what I'm really getting. So I'm going to write the first row first. I'm going to write it all. So my linearization, I've got negative 10, 5 plus, when you do matrix multiplication, it's the rows of this matrix dotted with the columns of the vector there. So it's 8 times x minus 1 plus negative 12 times y minus 3. And then you go down to the next row and you get 10 times x minus 1 plus 0 times y minus 3. And so then if you were to write the whole thing out, you would say that your linearization of x comma y, which is really just the first linearization on top, the second linearization on the bottom, or the linearization of the first piece and the linearization of the second piece. The top part is going to be negative 10 plus 8 times x minus 1 minus 12 times y minus 3. And the second row is going to be 5 plus 8 times x minus 1 plus 0. I'll write 0 times y minus 3, but we would probably just write 0. which is literally the same thing as if you'd done it the longer way, right? We could have found the partial with respect to x and gotten 8. I think I made a mistake right here. Sorry about that. That should be a 5 plus 10 times x minus 1. Sorry. Reading very uncarefully. That's exactly like what we did the first time, where we found the values and then we found the partial times x minus whatever, the partial times y minus whatever, same deal. So this is kind of the quote unquote faster way of doing it, where you just find your Jacobian and you multiply it by x minus the x coordinate, y minus the y coordinate, and then you add on f of x naught, y naught. So very, very generally, the linearization is equal to the function evaluated at x naught, y naught. That's this part right here. And then you add on your Jacobian matrix at x naught, y naught, multiplied by the vector x minus x naught, y minus y naught. Which I guess it's easier to see that if you look right here. Here's your function evaluated at x naught, y naught. Here's your Jacobian evaluated at x naught, y naught. Here is your x minus x naught, y minus y naught. Is it better to do it that way? I don't know. Is it faster to do it that way? Probably. So if faster is better, then yeah, it's better to do it the second way because it is faster. All right. Questions about this before we do more? Yeah, we'll do one more. Yeah, we got time. We got time. We ended 1:30, right? Yeah, 1:30. Okay. So the process is not terrible. I suppose we could throw on an extra question here. So now we could say use the linearization to estimate. And let's see, we were doing the linearization at 1, 3. So to estimate the vector valued function g at 1.2, 3.1. So all you're going to do at that point is plug in that value for x and that value for y. So we're going to say, well, here's our linearization. You can write it. I'm actually going to write it in the way I've written it up here. I'm going to write it like this. So my linearization at 1.2, 3.1 is going to be negative 10, 5 plus the matrix 8, negative 12, 10, 0 times 1.2 minus 1, 0.2, and 3.1 minus 3, so 0.1. Right, I'm plugging it, I'm looking right there to plug in my x and my y value. And now I'm going to multiply it out. I'm going to get negative 10, 5 plus 8 times 0.2 is 1.6. Negative 12 times 0.1 is minus 1.2. And then 10 times 0.2 is 2. And 0 times 0.1 is 0. So I'm going to get negative 10, 5 plus 0.4, 2, which ends up being negative 9.6, 7. I know I'm saying comma because often we write vectors, we write them in a different way. So ignore my commas there. So what we're saying here is that this vector valued function, which again, I'll show you right here was the vector valued function that we started with. G of xy was 8x minus 2y squared in the first entry and 5x squared in the second entry. If you're trying to approximate this function evaluated at 1.2, 3.1, this is a decent approximation of it, of each piece. And really you should just be thinking of the two pieces separately. Right? We're writing them together because it's convenient for us and because we're really trying to like get you ready for the stuff that's happening later in the quarter, where we talk about vectors more. But there's no reason why you need to do this all together. You could totally do it like we did the first one and do it separately. The only reason we're doing it all together is because it's faster. Okay. Yeah. Look at one more example like this, and then we will move along. So let's say we've got a function, a vector valued function, f of x, y, and let's say it's something like, sure. Let's say it's equal to, yeah, let's do that. E to the 3x times sine of 4y for the first entry, and e to the negative 4x times cosine of 5y, the second entry. And we're going to linearize this, find the linearization. This particular example, there's only really one nice value to linearize it at, and that's at 0, 0. E to the anything else is going to be a pain. Sine and cosine of anything else is probably also going to be a pain. That's not entirely true, but probably true. We maybe could have picked pi over 2. That might have been more fun. Oh, well, we didn't. So, all right. I want you all. So here's what I want you all. I want you all to find the Jacobian at 0, 0. So first find the Jacobian, which is just going to be the partials. And if you call this F1 and F2, then your Jacobian should be del F1 del X, del F1 del Y, and then del F2 del X, del F2 del Y. I want you all to find the Jacobian, and then after you find the Jacobian, and then find the Jacobian evaluated at 0, 0, which is just plugging in 0 for X and 0 for Y. It shouldn't all be 0 when you're done. You should get some actual not zeros. I'll give you a minute and a half. There are no product rules here, but there are some chain rules. It's 2 minutes. Well, let's take a look at our Jacobian here. So the partial derivative of the first piece with respect to X is going to be, oh, what's that? E to the 3x times 3 times 4. And the partial with respect to Y is going to be e to the 3x times cosine of 4y times 4. Similarly, for the bottom here, you're going to get e to the negative 4x times negative 4 times cosine of 5y. And over here, you're going to get e to the negative 4x times negative sine of 5y times 5. Just to be super clear, right? This is a matrix. It's a 2 by 2 matrix. There's no plus signs here, right? It's just entry, 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 entry. And then if we plug in 0, 0, our Jacobian at 0, 0 is going to be. So let's be smart about this. I don't want to write e to the 0 times 3 times sine of 4 times 0 when I know that sine of 0 is equal to 0 and 0 times everything else is 0. So I'm looking to see if I plug in 0, do I get 0? Oh, I do here. So I'm just going to write 0 there. Now over here, I don't. E to the 0 is 1. Cosine of 0 is also 1. So I get 1 times 4, which is 4. Down here, I'm going to get e to the 0 times negative 4 times cosine of 0, which is 1 times negative 4 times 1. And finally here, I'm going to get e to the 0 times negative sine of 0 times 5. The sine of 0 is 0. Oh man, pen all over my hand. So there is our Jacobian matrix. Neat. Now let's find let's write the linearization. So the linearization, I think we can fit it in here. Linearization, you don't forget the arrow, right? Because it is a vector valued linearization. So you should write the arrow on top of it. Is going to be the vector you get when you plug in the point. So if I plug in 0 for x and 0 for y, I'm going to get 0 and 1. Because e to the 0 times sine of 0 is 0, but e to the 0 times cosine of 0. Oh, you can't see on point 2, sorry. E to the 0 times sine of 0 is 0, but e to the 0 times cosine of 0 is 1. So that right there, that's your f of 0, 0, plus your Jacobian, 0, 4, negative 4, 0, multiplied by x minus the x coordinate, y minus the y coordinate. And then if you wanted to write this as one thing, of course I've run out of room here, you could write this as, sorry, I know it's kind of terrible to go back that way. L of xy equal to 0, 1 plus, if you multiply this out, 0, 4 times xy is going to be 0 times x plus 4 times y, which is just 4 times y. And then negative 4, 0 times xy is going to be negative 4 times x plus 0 times y. So if you want to write this as one vector as your final answer, you can write L of xy equal to the vector 0 plus 4y and then 1 minus 4x. So here's what we're saying with a lot of work. The linearization of this function at 0, 0 is just z equal to 4y. And the linearization of this function at 0, 0 is just z equal to 1 minus 4x. And you can use z or you can use L of xy. I was using z just to try and be a little more explicit, but that's what we're saying with all this work. We're doing two linearizations at once is really what we're doing. Kind of annoying, but it's not that terrible once you get the hang of it. Cool. Any questions about this, either regular linearizations or there's a question in the chat. Let's take a look. I like that it pops up like that. That's kind of useful. That made it very easy. Do we not use product rule for the derivative? Oh, so the reason we're not using product rule for the derivative is because if you're taking the derivative with respect to either x or y, right? If I would have to use the product rule, I'd have to have a function of x times a function of x. But I don't have that. So to use the product rule, you have to have the same variable function of it multiplied by another function of it. So some f of x times some g of x. That's why we're not using the product rule here. Essentially, when you're differentiating this first function with respect to x, you're treating this as a function, and sine of 4y is just a constant that's hanging out. So the derivative of e to the 3x times sine of 4y is just the derivative of e to the 3x, which is e to the 3x times 3. And then this sine of 4y gets to pretend to be a constant and just hang out. On the other hand, over here, the e to the 3x is the constant that's hanging out, and we're taking the derivative of sine of 4y, which is cosine of 4y times 4. Let's see. Cool. You're welcome. Yes. Other questions before we talk about the Chain rule. Okay. You might think like, well, James, we've already talked about the chain rule, but there's another chain rule, another version of the chain rule for multivariable functions. So I should really say it's for functions of functions, which is really what the chain rule is about, for functions of functions. So let's look at an example. I'm gonna try and not write all the words here. So let's say we've got the following. Pressure, which is measured in kilopascals, which I think is kPa. Yeah, sure. I don't really care. Kilopascals. Volume, you're welcome, yes. Measured in liters. And temperature, measured in degrees Kelvin, of 1 mole of an ideal gas are related by the ideal gas law. Those of you that are better at chemistry than I am, which is probably most of you, probably already know this. PV equals 8.31 times T. Approximately. That 8.31 is probably an approximation. The more general formula is PV equals nRT. That's all I really know, though. Like, I don't really know what N and R are, so don't ask me. It's not a chemistry class, it's a math class. Okay, so here's what we're going to say. If the temperature is 300 degrees Kelvin and increasing at 0.1 kelvins per second, and if the volume is 100 liters and increasing at a rate of 0.2 liters per second, how fast is the pressure changing? So let's start off by writing pressure as a function of volume and temperature. So we should divide both sides by V and get the pressure is equal to 8.31 times T divided by V. Or I would probably write it, I know I'm going to have to take some derivatives. It's probably going to be more useful to me to write it as pressure equal to 8.31 times T times V to the minus 1. So now I want to take the derivative of this, but the problem is pressure really doesn't just depend on temperature and volume, because temperature and volume both depend on time. As time increases, the temperature increases and the volume increases. So I need to do something other than just saying the derivative is like the derivative of each piece. So here's the idea. When we're trying to do this thing where we're going to use the chain rule, what we're going to do is we're going to draw a mapping of the functional dependencies. Question? It says 100 liters and increasing. I've abbreviated increasing as INC at 0.2 liters per second. So we're going to draw what's called a mapping of functional dependency. Meaning at the top, you've got the last piece of your function, what we're calling the function. The top, we've got pressure. And we have written pressure as a function of what two variables? It's not a trick question. Everyone can tell me. Right. Pressure is a function of temperature and volume. But although we haven't written it explicitly, we have been told that temperature and volume both depend on time. As time increases, the temperature and volume both also increase. So temperature and volume are both dependent on the variable T. I mean, yeah, I guess arrows are fine. So here's what we want to find. We want to find, well, the question is, how fast is pressure changing? They're asking us to find the rate of change of pressure with respect to time, right? If someone asks how fast something is changing, they're asking you, how is it changing as time moves forward? So we're really being asked to find dp dt. And note that I did say and actually mean dp dt. I'm asking to find the derivative of pressure with respect to time, not the partial derivative, because at the very kind of base level, pressure depends just on the variable time. But we have to take different paths to get there. So the way we do this is say, well, pressure depends on time, either by depending on temperature and then time, or volume and then time. So the path from pressure to time, there's two different paths. If I take this red path, I'm going to do the derivative of pressure with respect to time, which is a del P del capital T, because it's a partial derivative, because at that level, pressure depends on two different things. And then the derivative of time with respect to T, and it is a regular d capital T dt. It's really probably okay if you don't get all these del's and d's right, but I need to be specific and correct so that you see the quote unquote right way to do it. On the left side, our path that gets us from P to T is going to be first from P to V, so del P del V, and then from V to T, so dV dt. And then we're going to add all the paths together to get the overall derivative. So our derivative using the chain rule, and this is the chain rule, is del P del T times dt dt plus del P del V times dV dt. It is fairly standard to use uppercase T for temperature and lowercase t for time. So yeah, that's kind of what we got. Questions about this? Yeah. It's both. Yeah, we're using both. And don't worry, it's going to be, yeah, we have enough time for another example. We'll see another example where it might be a little bit more clear, but this example is kind of just to give us an idea of how this is working. Yeah, Jade. So where, right here? That's a del P del T. That's a D, that should be a dP. You're right, I didn't write it very clearly there. That should be dP dt. Sorry about that. Thank you. Okay, so del P del T, we have to actually find the derivative. So del P del T is equal to 8.31 times the derivative of T to the first is just 1, but then the V to the negative 1 hangs out. And yeah, similarly, del P del V, if I take the derivative of this with respect to V, the 8.31 times T hangs out as a constant, and the derivative of V to the negative 1 is negative V to the negative 2. Yeah. Yes, it did. Thank you so much. Gosh, I feel terrible. I'm making awful mistakes here. Yeah, good call. Thank you. Right, because I differentiated with respect to capital T, not lowercase t. Sorry about that. Geez. Thank you for keeping me honest. Please, if you see mistakes, keep telling me I'm making them because I don't mean to be, and we don't want to think the wrong things here. So we're going to rewrite our derivative dp d lowercase t is going to equal del P del uppercase T, which is 8.31 times V to the negative 1 times dt dt plus del P del V, which is 8.31 times T. I should have put the times negative V to the negative 2 times dV dt. But we want to actually find the derivative at the moment we've been talking about, right? They're telling us a lot of information. They're telling us T is 300 degrees Kelvin. It's increasing at 0.1 kelvins per second. V is 100 liters, and it's increasing at 0.2 liters per second. The increasing part tells us that 0.1 kelvins per second, that's how temperature is increasing. That means that's equal to dt dt, right? The rate that the temperature increasing is the derivative of the temperature. And similarly, 0.2 liters per second is equal to our dV dt. That's how fast the volume is changing. And we know that V is equal to 100 and 100 liters, and T is equal to 300 kelvins. And now we're going to jam all that into this to find our answer. So we can go ahead and say dP dt is equal to, instead of writing 100 to the -1, I'm going to write divided by 100. So I'm going to get 8.31 divided by 100 times dt dt, which is 0.1, plus 8.31 times the temperature, which is 300. And instead of multiplying by 100 to the -2, let's divide by 100 squared. And yes, I know there's a negative sign, so we'll put a negative out in front here, I guess, which is kind of annoying. I should have seen that earlier. And then finally, we're going to multiply by dV dt, which is 0.2. You could include all the units on a problem like this at this step if you wanted to. I don't think it's really in your interest. I think it's just good at the end to be like, oh yeah, things are changing with the right units. So when I find dP dt at the end here, it's going to be the rate of change of pressure per time. So it's going to be measured in kilopascals per second, right? Yeah, per second. So then we could do the math. The math part is not really the important part, but if you multiply this out and add it to, or subtract this, multiply it out, you're going to get approximately negative 0.04155 kilopascals per second. But really, at this point, it's just throwing stuff into a calculator and getting a numerical value. So let's look at another example, because it's good to see another. Yeah, we got that. We got 10 whole minutes. But there's a clock up there. I didn't even see that clock before. Let's look at something else. Something like f of xy equals. Oh yeah, go ahead. So that's actually a really good question, and I will say at this juncture, I don't have a great explanation for you for it. There is an explanation that involves some directional derivative stuff, which we haven't talked about yet, but we'll circle back around to that. I promise. It's just not, we don't have time for it today. But the short answer to that is, well, let's do this problem and I'll kind of talk about it. So let's say we've got this following function. Let's say f of xy is equal to x to the 4th times e to the 3y squared. And we're also given that x and y are both functions of t. X is equal to cosine of t. Y is equal to sine of 2t. And we want to find df dt. You could do this two different ways. In fact, this will kind of give an explanation. I've made life hard for myself here, but that's okay. You could do this in two different ways. One way, the harder way, would be actually just to rewrite the function as a function of t. So I could say that f of xy, knowing that x is cosine and y is sine of 2t, I could say that's f of cosine of t, comma, sine of 2t, which is going to equal cosine of t to the 4th power times e to the 3 sine of 2t squared. And that is f as a function of t. And so looking at just this, we could totally find the derivative. It's going to be a pain, but it's doable. So we can find f prime of t, or df dt. Okay, so it's going to be some product and chain rule stuff here. So product rule, the derivative of this, sort of cosine to the 4th, is going to be 4 times cosine of t cubed times the derivative of cosine of t, which is negative sine of t, times this stuff left alone, e to the 3 sine of 2t squared, plus, now we switch it up. We leave the first part alone, cosine of t to the 4th times the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So we're going to get e to the stuff, e to the 3 sine of 2t squared, times the derivative of all that. So the derivative of 3 times something squared is going to be 6 times that something to the first power, which I'm not going to write, times the derivative of that something. The derivative of sine of 2t is cosine of 2t times 2. Ah, that's awful. Let's do it the other way. The other way is to first write our path. So at the very top, you have f. F depends on x and y. But we know, we're told both x and y depend on the variable t. So the way this always ends up working, Jaslyn and everyone, is that to get from f to t, we have to go through x and y. So it's this path where you get del f del x times this path where you get dx dt. And then it's also this path, del f del y, times the rest of the path to get to t, which is dy dt. And then we add all the paths together. So df dt is going to equal del f del x times dx dt plus del f del y times dy dt. Okay, let's do it, and then we'll see how it's the same. So del f del x, looking at my, oops, sorry, you can't see the top function there. Looking at my function f of xy, del f del x is pretty easy. Del f del x is just going to be 4x cubed times, leave that alone, e to the 3y squared. Right, it's a constant as far as x is concerned. Times dx dt, looking over here, the derivative of cosine of t is negative sine of t. Plus, now we do the same thing except for the y's. Del f del y, so the derivative of x to the 4th times a function of y, the x to the 4th hangs out, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff times the dy dt, which is going to be the derivative of sine of some stuff is cosine of that stuff times the derivative of the stuff. Okay, so now let's, we don't usually want to actually plug in what x and y are equal to at this stage unless we're asked to, but I'll point out here we have 4 times cosine cubed. Here we have 4 times x cubed. Here we have a minus sine of t. Here we have a minus sine of t. Here we have an e to the 3 sine of 2t squared. Here we have an e to the 3 y squared, and y is sine of 2t. So this part here is the same as this part here. Similarly, x to the 4th is cosine to the 4th. E to the 3y squared is e to the 3 sine of 2t squared. 6 is the same as 6. Y is the same as sine of 2t. Cosine of 2t, 2. Oh, those are the same as well. So this example at least shows you that although we haven't maybe fully explained why we do this thing, it does work, right? This process got us the exact same answer, although we didn't write it all the way out with all the t's, that's fine, as doing it the way where you wrote the function fully as a function of t and then just differentiated it using gross product and quotient and chain rule. So doing it this second way is certainly easier. I mean, at the end of the day, if you wanted to get the same exact answer, you would need to go back and plug in cosine of t for every x and sine of 2t for every y. But it's an easier way of getting there. And so that's often why we do it this way. Also, some of the times you can't really do this first thing we've done, although often you can, but often you can't. Yeah, you would always do it the second way. Yeah. Doing it this first way is usually never a good idea because it's just much more complicated.